Hello, Chem112 students. This is Professor Miller. I am coming at you live from Boston right now. We're at a convention for one of my gaming clubs here on campus, and I don't have my headset with me. Usually the sound quality is a little higher, so you might hear some background noise. I'm sorry for that. But I realized that the equilibrium videos I tried to upload before I left didn't upload and didn't save. So here we are again. So we're talking about chapter 20, which we did discuss a little bit in class. I'm going to review that part of the discussion and then pick up with hopefully some new information for you. Although I suspect hopefully by now you've read it in the book and you've done some problems with it. You certainly did it in lab. So this should just sort of help clarify any questions you have. And of course, if it doesn't, you should always feel free to email me. Okay, so first off, we need to remember some of the stuff from chapter, well, actually, I think this is not 15 anymore in your textbook. I actually think this is the one we call 19. That's where we learned about electrolytes, right? So that was like the crux of that chapter. And there's a lot of extra really cool information in there about like how to tell when something is going to precipitate, if it's a strong electrolyte or a weak electrolyte. All of that stuff is important here, right? And so these three types of chemicals are all electrolytes: acids, bases, and salts. And just real briefly, remember that acids have a low pH, which means high H+ concentration, and bases are exactly the opposite thing. We also know that acids taste sour and bases taste bitter. Okay, so that's just sort of a helpful way to remember that these compounds are things that are all over our environment. They're in our food. A lot of bases are poison. For example, different kinds of poisons tend to be bases. A lot of our cleaners are bases too, and you would never eat those. That's a bad plan, right? So, but all of them are electrolytes. So like, for example, if you plug a battery and a light bulb into, bare wires, kind of like what we did in lab, into a container of bleach, it will conduct electricity because it's a base. It's mostly water, but there's a bit of base in there, and that's sodium hypochlorite. That's what makes bleach clean so well. So really high pH being a base, and don't eat it, okay? Bleach is not food. I hope you know that. I'm sure you do, but I just have to say that. But if you did, it would taste really bitter because it's a base, and that's what bases are. Okay, so those concepts from that chapter are important here in our equilibrium discussion. So the first thing we're going to try to do is explain what an equilibrium even is, and we're going to look at a couple of examples to do that. We're going to look at something we've seen before when we were talking about how things dissolve, and so a slightly soluble salt, other than a tongue twister, this is something that dissolves a little bit, slightly soluble, dissolves a little bit in water, and that turns out to be an equilibrium. And so we did talk about that way back in something like chapter 13 in the beginning of the semester, but we're going to look at a simulation about that again. And then we're going to look at an actual chemical reaction and see how that kind of works on the particle level. It's a simulation of a chemical reaction, technically, right? So it's going to help us picture what's happening. And then finally we're going to try to look at a general reaction and make some observations in general. And then we're going to try to examine the effect that temperature has on an equilibrium, because it's different depending on the type of reaction that we have. Okay. All right, so reviewing chapter 15. First off, we have the definition for acids that was developed by Bronsted and Lowry, and they think of it as, this is supposed to have a space in it. Hang on, space right there. Okay, well there's the beauty of doing videos rather than teaching live. I just fixed my typo. I don't know why it showed up that way. It should look like this. Bronsted-Lowry acids are proton donors. They like to give up protons, right? They make H+. And bases are proton acceptors, because it turns out protons can't just go out into the universe alone. They are a naked positive charge, and it would be very vulnerable that way. So Bronston and Lowry think of these as two things that go together. You've got an acceptor and a donor. The acceptor is the base and the donor is the acid. Arrhenius had a simpler definition. He just said, hey, when I put this stuff in water, it makes hydrogen ion. Turns out that's not actually true, because in all the times we've taken various pictures in various different ways of particles, we have never seen a single H plus just like existing on its own. So we don't have any evidence that that's true. It is a simpler way of thinking of things. So if I'm just trying to figure out if it's an acid or a base, I do look for this H plus. And a base would have the opposite thing, OH minus. Okay, this is hydroxide. This is hydrogen ion. Also, chemists are tricky beasts, so sometimes when we say hydrogen ion, we're talking about hydronium ion. It's the same darn thing. All you do here to get to a hydronium from a hydrogen is you add water. And since it says it's in water, we think this is actually more plausible for what might actually be happening. So sometimes we write hydronium ion, or sometimes we write hydrogen ion, and they are in fact the same thing. Okay. Glad we cleared that up, because it's totally crystal clear now. We do know that acids and bases can be weak or strong depending on how many ions they produce when you put them in water. So something that is strong is going to light the light bulb up all the way, meaning lots of ions are running around, right? So in order to get the light bulb to light up, you got to have a lot of positives and negatives charges running around so they can carry electrons back and forth. And so a strong electrolyte would do that. Strong acids and strong bases are strong electrolytes. So that matches, that makes sense. Weak ones are weak electrolytes, because it means they don't have very many ions to carry charge around. Okay, and then so kind of related to the Bronsted-Lowry definition here, when an acid gives up a proton, we produce its conjugate base. All right, so conjugate is like a pair, they go together. And they're kind of opposites. If we have a really strong acid, like say HCl, when it donates the proton, the thing that's left over is called its conjugate. Well, yeah, I'm going to take that out. We haven't talked about that yet. Its conjugate would be the thing left over after you give away a hydrogen ion. So here's our conjugate, chloride ion there. It is not a good base. It's a very, very bad base, because the HCl is such a strong acid. It means this chlorine is not very good at accepting hydrogen ions, which makes sense, because if it were, then we would be able to write this reaction going in two directions like so, and we can't. Okay. So similarly, if we have a strong base, it's going to produce a very weak conjugate acid. An example of that is any of the group 1 and 2 mineral acids, except for lithium hydroxide. Lithium hydroxide is a weak base. This is a strong base, though. That means that when I put it in water, it's going to form a whole bunch of potassium ion and a whole bunch of hydroxide ion. So what we're saying here is this being such a strong base means that its conjugate is really weak. And then we've got some equations to describe pH. I give these to you, but you do have to know how to use them. You are going to have these questions on your final exam, and it is really, really important that you know how to do logarithms and exponents correctly on your calculator. It's different for every single calculator, and I can't teach you how to use your calculator correctly during your final. So while you're used to having different resources at home for your quizzes, because mostly that's online, you need to be able to use the actual calculator that you're going to have on your final exam. And remember, that cannot be your cell phone. Okay, so you should be prepared for that. All right, so on this slide, we're going to try to answer a few questions by watching a simulation here, and this is related to forming a solution. And so the first question is we want to figure out what is the process that occurs initially called. Okay, so first we just shake a bit of solid in there. All right. Oh, there's the process. Okay, that was the process. What we just saw right there in the beginning was essentially all of the solid that I put in there, it dissolved. Now there's actually a number of ways. This is a salt, which means it's ionic. It's a metal, strontium in this case, and nonmetal, which is phosphate. So we have, you know, strontium and phosphate ions in there somewhere. I don't know what charge. I think strontium is a 2+, I'm going to guess, because it's in group 2. I don't have my periodic table here because I'm in Boston and I actually don't usually carry it around, but I'm pretty sure it's a 2+. You should check that, see if I'm wrong. Okay, anyway, so we call that process dissolving. And of course, if I were looking at this with my eyeballs, it would look like plain old water. I wouldn't see anything because the solid disappears, evidently. And so now here's a place where a lot of people have a misconception. When I show them something dissolving, they'll say that it melts. And I want to be really, really clear about this. That's not what dissolving means, okay? So when you melt something, say like water, if I take a piece of ice and I melt it, the molecular structure, what's happening on the particle level, has not changed. It's still H2O, 2 oxygen, oh, that was wrong, 2 hydrogens attached to 1 oxygen, and all of them kind of close together. That's what is happening. It's just a matter of the speed of the particles changes when you go from a solid to a liquid, of course, a liquid being faster moving. So I just want to be clear that when it looks like something has disappeared, that's not the same thing as melting, okay? If we look at this picture, for instance, let me just show you. Here's the solid, right? And so the phosphates and the strontiums, pink and green, are closely attached to each other. That's what makes this a solid, and they're not like moving relative to each other. They all stay sort of clustered together. The stuff in the solution separates, you know, so you got different ions in different places, and that's what dissolving is. So there's a couple of other phrases that are used. One of them is dissociate or dissociation. Now, that just means to separate, right? So the positives and negative charges are not hanging out together, right? So if I want to, like if my friends are doing something that I don't agree with, I'll dissociate myself from them for a while until they come back to my way of seeing things. Associate is the opposite of dissociate, right? So associate means to come together. Dissociate means to go apart. So sometimes we say dissociation, and sometimes as long as the particles that are being formed are ions, we can say it ionized, or it has undergone ionization, the process ionization, right? So ionized is like the past tense version of that. So we could say, oh, that solid ionized because it formed 2+ and a 3- particles, right? So it forms ions. Okay, so the next question, these are all numbered number 1. I don't know why, that's kind of weird. Probably because I have to switch to PowerPoint to do these videos, and it doesn't always agree with the program I used to write the video. Anyway, so number 2, our question is, when is the solution saturated? So this is a review of vocab from the chapter on solutions. And okay, so not saturated yet. What we have done is ionized that solid again. So I'm going to put a little more in. Nope, still not. Quite a bit of ions in there. Now it's saturated because now at the bottom I have some solid chunks kind of floating in here. And I can look over here and count them. We have about 8 or 9 solid particles. That's the bound. And we have like about 45 strontiums that are dissolved. Ish. Fluctuates a bit, but it's pretty much staying 45. Now, in the really real world, if I looked at this stuff, I probably couldn't tell that it's saturated because the key I'm looking for is that there's solid on the bottom that is visible. So of course, you couldn't see like, you couldn't see like 10 pieces of something. It's not big enough. So if this were really a solution, I'd probably end up putting in way more than I needed to in order to create a saturated solution because I gotta be able to see that this on the bottom for it to really count as saturated. Okay, so we consider a solution saturated if you can see solid on the bottom or floating in it, I guess. If you can see solid, in other words, that's the important criterion. All right, so let's watch this. The solid and the, oh, hey, cool, we got some hexagons forming. This is a cool thing about strontium phosphate. It's a really complicated molecule. a lot of, and a lot of pieces to it, but it forms this hexagonal crystal structure, which is just really cool. But when we watch this structure, like one of these pink ones just appeared out of nowhere, and oh wow, so we just got another green one. So these are not required to stay in place. This shape overall is kind of fluctuating with time, especially around the outside edges. The middle doesn't change a lot, but the outside edges seem to change quite a bit. But our total number of dissolved and bound ions is not fluctuating all that much. They're pretty much staying around 46 ions, just like it was kind of when I only had 9 bound. So I want you to take a second and just write a little prediction here. Tell me what's going to happen if I put in more solid. Is the number of dissolved ions going to increase? Does it decrease? Does bound increase? Does it decrease? Does it stay the same? Okay, so pause the video and make your prediction. Okay, so I'm going to put a whole bunch in just to make sure we can tell a difference, right? And we gotta wait for a second. Equilibrium doesn't happen instantaneously, especially in a simulation that's supposed to show us like particle level interactions. But I think we're at equilibrium now because the numbers here are kind of consistent, right? So we're still sort of hovering around 45 dissolved strontiums. So if your prediction was that the dissolved would increase or decrease, that it didn't. It stayed the same. And that's because, well, we've already reached a saturated solution. I've dissolved as much strontium in there as I can possibly fit. The water isn't going to fit anymore. The only way to get this number bigger is if I add more water, which would of course dilute it out and dissolve some more of the solid. So that's interesting. The bound did increase because of course I put in more stuff in it. If it can't go into dissolved, it's got to go into the bound. It's got to go into the solid phase. So when we add more, the prediction, whatever your prediction was, but when we add more, what we see is that the only thing that changes is you get more bound. Okay, so it was a big clump on the bottom, and now we got this beautiful pattern again. Hexagons, looks like a bee's hive, And so if we could just follow one ion around all day and watch what it does, what we'd find is that sometimes it's an aqueous ion. It's like hanging out free, not attached to anybody. And other times, oh, like that one, it precipitates into the solid phase. Now that's interesting. So on an individual level, no single ion has to stay solid or aqueous. They can go back and forth. But on the level of the entire sample, we always have around the same number of dissolved ions. It doesn't change dramatically. So what this tells us is if one of them precipitates, another one at the same exact moment has to dissolve. Those are the two processes happening. So you can think of this as an equilibrium reaction. Okay, so strontium phosphate is actually, well, pause the video, see if you can write the formula for it. Okay, here it is. So +2 over here and a -3 over here. It means the common denominator is going to be -6. Common factor, actually, I think. But anyway, so -6 for this side, +6 for this side, and that's how we get it to balance. So that's what strontium phosphate as a solid looks like. These reactions are going forward and backward at the same time. That's just sloppy. Let me fix this arrow. That's what we call an equilibrium. It means that the reactants and products are simultaneously existing. It's kind of zen when you think about it. So we draw that with an arrow that goes forward, it's a half arrow, and backward. Right? I hope you can draw better arrows than I can on my computer, but there it is. And so when this ionizes, it's going to produce particles that are separate, the charged particles. So strontium is a 2- charge on the periodic table, and I have 3 of those. That becomes a coefficient over here because it's 3 ions attached to 2 phosphate ions. So they're not attached to each other. They're attached to the phosphate. They wouldn't want to hang out together because they're all positively charged, and they don't get along. And we also produce 2 phosphate. Now I don't break off the 4 because that's part of the polyatomic, and I can find those on the back of my periodic table, which you will have for the exam. So when you see something funky like this, look back there and be like, oh, what charge does that have? Does the O4 part of it, or does it come off, whatever? So look around for that. That's also when I name things. I got the phosphate from the back periodic table. So here's our equilibrium, right? We have solid and we have a bunch of aqueous ions, and they go back and forth. If one of the particles decides to dissolve, that means these guys have to go back and form a solid. Otherwise, these numbers would be changing all the time, and they don't. So, how do we know when the solution was in equilibrium? I said it takes a few seconds, a few minutes. It takes some time. But the key here is I looked at the concentrations, and they were stable, right? It stayed around 45, 46, 47, something close to that of the dissolved strontium pretty consistently. And that's kind of a key aspect of equilibrium. Now, let's go back and look and see. It's still running in the background. Oh, look, the pattern's different. It's still hexagons, but it's a different shape. We still have roughly the same number of strontiums as we had to begin with. So that's interesting, but we'll also notice that the dissolved and bound, in other words, our products and reactants, they don't match. They have different concentrations, and even our two products here are different, and that's because they have different coefficients, right? There's 3 strontium for every 2 phosphate, so you wouldn't expect them to match concentrations. So as far as what is not equal, concentration of the products and reactants are not equal. Okay, so that's not what equilibrium is referring to. Yeah. The thing that is equal is, I guess you could say, how fast the forward, oops, that's a forward arrow, and reverse reactions are. And the reason I can draw that conclusion, these are two separate ideas. The reason I can draw that conclusion is simply because I watched particles that precipitated, but the concentration of ions did not dramatically change. So that means that something had to dissolve if another thing was precipitating. Otherwise, your concentrations would have been changing over time. Okay, so the next simulation is an actual chemical reaction. We want to answer some questions about that. Okay, so here is our chemical reaction. Right now, just a little question here. I'd like you to jot the answer down, what you think the answer is. Why is our box signifying a reaction at 0 Kelvin right now? So take a sec, pause the video, answer my question. That, of course, is graded. All right, so here's what I'm going to do. I am going to put in 100 reactants. All right, so this is the simplest kind of reaction. We're going from one thing, converting it to another thing. So this is a generic reaction. And the size of these letters up here gives us a relative amount of stuff. So let's see what happens, all right? And I'm going to put them in around room temperature, so a little bit warmer than that. So we got a big A and no B. Oh, there's a B. What was that? Oh, wow. Okay, wait. Okay, so what's happening at this point is we started with 89A. I'm looking up here at the count, 89A, and 11B has been formed now. So I started with 100A, and all of them so far have been going forward, right? So we're going from lots of A producing some B. So we call that the forward direction of the reaction. So initially, the forward reaction, that says RXN, that's an abbreviation for reaction. So the forward reaction is happening. In other words, you could think of this as A forms B. That's what we see. That rhymed. I'm going to write a children's book about chemistry. You guys are going to love it. Just kidding. All right, so we have a bunch of A's, and so they're going to form some B. All right, and so I'm gonna resume the simulation and see what it does. Oh, what was that? Did you guys see that? Let's keep watching. What just happened? This guy up here just came from way in the right field all the way back, and as soon as he got over this line, he turned back to being an A. So that was one of the first examples. I think there was one more, but this is one of the first examples of the reverse reaction occurring. So after a few minutes, we see that the reverse reaction occurs. So in other words, B forms A. All right. So the question is, are we at equilibrium at this point? Let's keep it rocking and rolling and see what happens. Okay. By the way, here's another question to ponder. Is this reaction being shown here endothermic or exothermic? Take a second and just like over here, endo or exo? And maybe even tell me, how do you know? How do you answer that question? What does it mean? Okay, so let's see. We got 76 A's and 26 B, 27. Well, if it stays at 26 or 27 for a while, I guess I'm done, but it's not. It's going up to 30 already, just while I'm sitting here talking. Okay. I'm going to let this sit for a couple minutes. It takes a little bit of time for equilibrium to be reached. I'm going to pause the video for you until the computer decides that our simulation has reached equilibrium. Okay, before I show you the results, I know you're on the edge of your seat. You haven't been waiting very long. I have. That's the magic of video. But before I show you the answer, I want you to tell me whether you think, so here's another question. I'm going to write this one in a different color. I want to know whether you think there's going to be more A or more B at equilibrium, and why. Just find some space. I know it's kind of a cluttered slide, but find some space to think about this real quick. Pause the video. Okay, so here's the result. Dun, dun, dun. We have about 38 or 39 A's and about 60 some B's. It doesn't fluctuate all that much. Goes up, goes down, goes up, goes down, but it's overall staying around the same. Okay, hopefully you predicted that B would be more dominant. It's about 60% B and about 40% A. Because, and then the reason that is true is kind of about this energy, right? So this is an exothermic reaction. There's an answer to one of the questions. Because our reactants are higher in energy than the products, right? So this is that reaction diagram that we've seen before. And since the products are lower, so since this is an exothermic reaction, if you look at this, the forward reaction has a pretty small hill, right? So like if this was my house and I had to ride my bicycle to work, it's kind of fun, you know, on the way to work. But then after a long day, I have to go all the way back up this big hill. So in the reverse direction, the energy is a bit higher, which means they kind of get stuck down here, right? Like if you had the option of not bicycling all the way back up this hill to get home, you might just chill out at work, you know? Well, maybe. They'd probably make you keep working. So maybe that analogy falls apart there. But if I make these energy levels the same, or at least as close to the same as I can, I think that's about the same, we could watch it. I'm gonna just heat it up a little bit so this happens a bit faster, right? Okay. Eventually, this is probably going to come to a 50-50 mix, right? Now it's changing a bit. Not sure, it's a little slow. It would be a 50-50 mix. So we'd have, in other words, an equal amount of A and B, and that would happen because the energy of A and B are the same. So anyway, the relative energy level helps us predict how much, if we're going to have more product or more reactant, right? So exothermic is going to have more product. If we had an endothermic reaction, something like that, we're going to end up with a whole bunch more A's because they're going to get stuck on this hill. Okay, so cool. Oh, and here's a question. Let's say I have a catalyst, right? So a catalyst, what a catalyst does is it lowers this activation energy. It lowers this hill. And I'm messing with my computer, right? So if you lower the hill, it's easier to go in this case in the reverse direction, but it's also easier to get back up that hill. So a catalyst doesn't actually change anything about the concentrations of things. It just means that the equilibrium happens faster. You know, you can go back and forth easier. But it goes down on the, both directions, not one or the other. Okay, anyway. What I was waiting for is that the equilibrium stopped when concentrations are stable. Now, I'm not saying they were equal, right? In our case, it was like a 60-40 mix of B and A. So that's not equal, right? They are stable. They stop changing. It stays right around 60 and 40. The forward reaction never stops. Sometimes, if you go rewind the video a bit, you can see that the reaction is still going forward, and in the reverse, some of the red were becoming blue or green or white, whatever that color is. Anyway, they kept going backward. So the two reactions occur simultaneously. They never ever stop. In fact, here, look, this is our simulation again. Look, still going. Oh, there was one. There's another one. Back and forth, back and forth. And it's going to keep doing this pretty much forever. Okay. No. Concentrations of A and B are not the same, except for when the reactants and the products have the same energy. Then they would be the same. But that's a pretty rare, unique case. Things generally don't have the same energy. If they did, they probably wouldn't react that way anyways. All right. And then, so what is equal at equilibrium? The speed of the forward reaction and the backwards. So in other words, we watched an A turn to B and another B turn to A at the same exact time. So the short way of saying that is that the rates forward and backward are equal. Right? In other words, as A forms a B has to form an A. They got to go back and forth. They are constant at equilibrium. Whenever I messed with stuff, they would be non-constant, but we've been at like 70-something and 20, 30-something here for a while, so that's pretty constant. By the way, this is not a statistically significant sample. 100 particles is nothing. We wouldn't ever study anything that small in the lab. So this is a simulation to give us a general idea of how equilibrium works. In truth, if we had an actual laboratory-sized sample of atoms, it would be a big number, of course. Because it's such a big number, these fluctuations don't appear at all, right? So your concentrations are completely constant. It looks like it's not in the simulation, but that's because we're only using 100 particles. If I put in a mole of particles, then it wouldn't fluctuate at all. You would not see that change. Okay. Now here's a question. We thought about this in class. Do you think you could reach equilibrium in a combustion reaction? That's burning, right? And so burning requires oxygen because there are no barbecues in space. Could we somehow make it go forward, which is the way we traditionally think about it? So that would be, producing CO2 and water. Let's see, how many water? We need 2 of them. Okay. And we need 2 of those. I think that's right. Yeah. So here's the combustion of methane. This is one of the things that you might be paying National Grid for in addition to electricity. We call it natural gas. And so the question is, if I don't want to pay, I don't want you to think that's cobalt. That's carbon dioxide. There we go. If I don't want to pay National Grid anymore, is it possible to capture all the carbon dioxide that I burned up? Okay, anyway, so if I could capture all of this, is there any way I could make it go back to oxygen and methane? Because then I could burn it again, right? Oh, this is another thing. It produces a lot of heat. That's what we use it for, to heat our houses. So I can write energy as a product there because I know it's hot. It produces heat. So in order to get this to go backward, not only would I have to capture all the CO2 and all the water, I'd also have to capture all the heat that was made and put it back. And so if I did that, and if I got these gas particles close enough, the CO2 and the water, if I did that, I could theoretically make the combustion go backward. It's not very practical though, because again, the reason we use it is to make heat, and if I have to put the heat right back, it doesn't really make any sense, right? And it produces a lot of heat, so that hill is going to be really big. So like if we sketch, right? So going in the forward direction, it's a little teeny bit of energy, a little spark to get it up there, and then we fall down and collect a whole bunch of products. To go in the reverse direction, we got to put all that heat we got out of there right back, and that's going to take quite a bit of work. But in theory, you could. It's possible. Costs a lot of energy, but you could do it. All right, so take a second and just jot down some characteristics from our simulations. Okay, pause the video. All right, I'm going to assume you did that. I'm going to give you my characteristics. Hopefully you have more than just mine down, because that's what I'm looking for. You should have written down some ideas. The first thing I noted is that concentrations are stable. I don't know why my R has an extra loop-de-loop, whatever, air. The concentrations are stable, but not necessarily equal. It's hard to write on this, so I'm just going to abbreviate everything. Okay, so that's one good thing to note. Like, individual particles don't stop changing, so they're like going from A to B or B to A or solid to aqueous, whatever. So this is a state that is often referred to as dynamic. On an individual level, the particles are like able to go back and forth. But again, the concentrations are stable, so it means if one goes one direction, another one has to go backward. Okay, and another factor that is important is that it's continuous. You know, it doesn't ever stop. If we go back to our little stimulation here, it's still going. Some things are still going forward and some things are still going back, but overall our concentrations tend to hover at 70-30 for this particular equilibrium. It will be that way if I left it on my computer and look at it tomorrow or a week from now. It will still be the same thing. Okay, so it's continuous. And then finally, the part that's equal, the reason we call it equilibrium is because the rate in the forward direction is equal. That's the equal part to the reverse, right? So using all of these characteristics, try to come up with like a 1 or 2 sentence definition of equilibrium. Use your words, not your book or the internet. All right? Come up with something, you know, that you can remember, something that will define what equilibrium is for us. Okay, so this is a photograph of some military members who are, you know, having a team building training day. So obviously these guys are playing tug of war. These ladies and gentlemen are playing tug of war right here. And it doesn't look like any one particular side is really winning. So I don't think either one's in motion. You can kind of tell because they're all like leaning away from each other. So I think that they are not really in motion. They're sort of equal, you know, pulling equally hard. And so one tactic I have seen successfully used is if like these guys just suddenly drop the rope. What's going to happen to the other team, right? They're pulling, and then suddenly there's nothing on the other side. What's going to happen? Well, they're going to fall over, right? They're going to fall down. And of course, the reason that works as a tactic for tug of war is once they fall down, the other people can pick up the rope and pull it, and they win. It's kind of cheaty, though. Okay, it's not really the spirit of the game, but I've seen it done. Okay, so what if instead of just letting go, what if we hook a bulldozer up to this side, which of course is much stronger than, you know, 10 people? What would happen then? Well, everybody would go flying that way, right? They'd go flying across the field, and they would lose. The only way to stop that from happening is if, in order to get back to balance, we got to hook another bulldozer up, right? And then we're having a tug of war game with 2 bulldozers on it instead of about, like, you know, 15 people. Okay. Now let's think about this in terms of a chemical reaction, right? So right now our system is at equilibrium. It does not mean we have an equal amount of reactants and products, because we don't. We don't even have an equal amount of reactants comparing those two to each other, right? So this reaction here is A plus B. It's an equilibrium, so I'm using the 2-headed arrow, and it's going to form AB. So that's our overall reaction. And so in the beginning, we start off here at equilibrium with 3 reactants and 1, 2, 3, 4, 5 products. Okay, and we could tell this was at equilibrium because if I wait a few minutes and I count them up again, it's going to be 3 of these and 5 of those. Now it might be like 2 B's and an A, you know, but it's still going to be 3 to 5. Okay, so the ratio of concentrations of products and reactants in this case is 3 to 5. No. What if I mess it up? What if I put in a whole bunch of extra B's? So that's going to look like this. This is no longer a balanced equilibrium. Now we've messed it up. We screwed it up. That's called a disturbance. We disturbed the equilibrium by adding reactant. So now we got like a whole bunch of reactants. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, like 14 reactants, and only like still the 5 products. So this is in the very instant that I drop in all this B. And so the interesting thing about equilibrium is that nature will kind of automatically fix it, okay? So in order to fix it, we got to get rid of or use up some of this reactant. We got too much of it, right? We have 14 instead of the 3 that we're supposed to have. And so what it does is basically reactants collide more often than they were, which means that you produce more AB. Okay, so if we wrote this as a reaction, A plus B, instead of having an arrow where they're equal in size, we would be showing it more like this, right? Teeny bit goes backward. Mostly it's going forward to make more of the product. So we're going to use up some of the reactant and produce product. So what that means is if we got a big arrow, you know, we're making a lot more AB than we are A plus B, is the rate forward is faster than the rate back. Just for a little while. Just for a little while. Until we get back to a place where we are at an equilibrium again. Okay, so for a little while we go fast in the front direction. Okay. And now we have 1, 2, 3, 4, 5, 6 of these, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those. In the beginning, we had 3 to 5. If we simplify 6 to 10, you end up with 3 to 5 again. So, when we are back at equilibrium, the ratio of reactants to products goes back to being exactly the same thing. Okay, that's another way we can tell if we're at equilibrium. If that ratio is constant and then we do something to disturb the equilibrium, it's going to end up back to the same ratio overall. Okay. When we say that the forward reaction rate increases, what we're really saying is that it has shifted to the right, meaning it's making more product than reactant. Okay. And we know that it's back at equilibrium when the concentrations are constant. Okay, that's the key. Okay, so we've been talking about generic reactions and models and all this stuff, so why does it matter? So here's an example. There's this little thing called altitude sickness, and if you have ever had the fun of being at a high altitude, you've probably felt this for any length of time. I had a student once who shared with me that she had gone to Peru on a mission, and Peru has really high mountains. It's some of the tallest mountains in the world, and people live up there, and so she was there trying to help them. And she told me she felt sick for months, like having the flu that just goes on and on and on for months and months, and it was horrible until suddenly one day she felt like much better. Okay, and so this is a problem. And this problem involves proteins from our blood that are called hemoglobin. So hemoglobin is really cool. With these cartoon representations for what proteins look like. Biologists like them because they don't want to picture all the different atoms because there's just like a lot of them. So we draw these little cartoons to kind of show the shape of a protein. And the important part of hemoglobin, which we abbreviate in a chemical reaction as HB, is the iron. There's 4 iron groups called hemes. They're sort of iron surrounded by some nitrogen. These are the ones that are responsible for hanging on to oxygens in our blood cells. And so they kind of, those 4 exist at the sort of dip in a red blood cell. And so if you recall from the osmosis chapter, we learned about how important the shape of this is, and that has to do with where those irons are placed. So shape matters. And the irons have to be present for them to carry oxygen. That's why anemia sucks. yeah, and so they hold on to the oxygen, and then by forming this complex, hemoglobin with 4 oxygens stuck to it, basically an oxygen at each iron location, and then it cruise to the muscles or the brain or the organs or wherever that needs the oxygen, and we have to let it go. We have to have gaseous oxygen for our metabolism to work. All right, so basically this happens in your lungs where there's lots of oxygen. We form our complex, and then in your muscle tissue, it's got to go back so you can use up this oxygen here. So it's kind of an equilibrium. All right, and so people who go traveling to high altitude places frequently get sick because of an imbalance in this equilibrium. Okay, and mountain climbers and cyclists both use this. Both experience this, and so the question is, how can we fix it? Okay, and this is an important thing here. We have low oxygen pressure, and so here's why. I want to show you this. Okay, so let's just say, for instance, this is my world. Here's the ocean. I'm not an artist, guys, so just like use your imagination here. Here's my mountain. Okay, there's Peru, I guess. If I have a person, he'll be dressed in red. If I have a person at ocean level versus another person who's at the top of a mountain, which one has more oxygen available to them? Well, let's see here. So as it turns out, we have a limited atmosphere, right? So here's our atmosphere. This is all air that contains oxygen in it. So when we look at it this way, which one of those two has more oxygen between them and space? Well, oops, that's still a highlighter. That's going to be weird to write with. So from here to here, we have a whole lot of oxygen. Between here and here, we have a whole lot less oxygen. So when we say low oxygen pressure, what we mean is there's physically less oxygen available to the guy on top of a mountain. Okay, and so that's kind of a strange thing. We kind of wonder, like, why would that make you sick? Well, let's see if we can explore that a bit. All right, so first I want to show you a little video. This was made by Tim Thomas and some of his students, and you did this basically in labs, similarly anyway. Hang on, I gotta pull it up. Okay, so chromate is a yellow substance, and it exists in an equilibrium. Whenever we put it into water, it always does this with its conjugate dichromate. Okay, and dichromate is orange, so this is a really visible reaction. It's pretty cool. So I remember the name because chromate has 1 chromium and dichromate has 2. Right, but these are on the back of your periodic table if you forget the names. Right, here's chromate, so these go together. Here's dichromate right there. Okay, so if we happen to have an equilibrium where it is mostly chromate, so here's some dichromates, these little darker circles are the dichromates, but it's mostly chromate. We have to have a few there because it can't just be reactants, then it would shift around, right? So we start off with mostly dichromates, right? Oh, sorry, that was wrong. Just a couple dichromates and mostly chromates. What color would this solution be in that condition? Okay. And then the next question is, if we add a bunch of HCl to the equilibrium, what are we doing? What are we adding? So what I'm looking for here is the fact that HCl is basically 2 pieces, right? So if I put HCl into water, it's going to ionize because it's an acid. It happens to be a strong acid, so it's going to make a lot of ions. It's going to make some hydrogen ions and some chlorine ions. So I look through my equilibrium here and I see whether either of those things are involved in our reaction, and hydrogen is involved. It's right there. So basically by adding HCl, I'm going to be adding hydrogen ion. And so that's like adding too many reactants. Now I've got to use up some of those reactants. So make a prediction what you think is going to happen. Let's put our prediction right here. What happens to the color of our solution by adding HCl? Okay, so here's our video. Starting off yellow, adding the HCl. Aha! So it turns orange. Oh, that was Mr. Thomas talking if you heard that. It turns orange. Okay, so if it went from yellow to orange, that means the reaction shifted to the right. We made more product, and that makes sense. It's kind of similar to the dumping a whole bunch of B's situation in. I have too much reactant. The reactions have to shift forward to make product. And we get back to the same ratio because I, at the end, still have more hydrogen than I started with. I have less chromate because that got used up, but I've made some dichromate, so it kind of balances out, right? If we add up all the products and all the reactants, it's going to be the same ratio as it was. Okay? So in order to fix the disruption, it has to shift to the right, meaning the forward reaction goes faster. And so we see an orange solution. Okay. New scenario. Now we're starting off with a lot of dichromate, just a few little yellow spots for chromate. All right, so we have a large amount of dichromate. And the question is, what happens if I add sodium hydroxide? Sodium almost never does anything in a solution, so we're going to pay attention to the hydroxide, the base, okay? And so the only reaction that bases have that we talked about in the electrolyte chapter is they like to react with acids. So anytime I have a base, I'm looking for an acid to put it with. An acid is just H plus or H3O plus, depending on my mood, and it would make water. Okay, so if I have a whole bunch of H pluses laying around, like, I don't know, say these ones, they can react with the hydroxide, okay, which would mean we are decreasing the amount of H plus that's there. So instead of increasing it like we did in the last problem, now we have decreased it. So we're decreasing the amount of reactant we have, which means now I have way too much product. Okay, So you could say decreasing H plus or reacting with H plus, however you want to phrase that. But basically, we've disturbed it by taking something out of the equilibrium up here. And I know that that's kind of what's happening because if I put OH minus in there, it's not going to hang out with chromate. That's a negative charge. That's a negative charge. It might hang out with water, but if it did, it would just take the hydrogen and it would make OH minus again. So that doesn't change. Like, that's kind of the position we started in. So that one doesn't really help. But I know that if I have a negative charge, it's going to be attracted to a positive charge. So that was my logic here. Okay, so if we don't have enough H plus because I removed it, what's going to happen? Make a prediction, and then I'm going to show you. Okay, so starting off orange, we add our NaOH. Oh wow, so it got really yellow. Was that what you predicted? Okay, so tell me, what direction did it shift to do that? We went from orange originally to yellow. Is that a left shift or a right shift? And our solution turned yellow. So that's our evidence for our reaction. Okay, and then I can explain it. Okay. Now, oops, I skipped a slide. Back to the same idea here. So what is the cause of altitude sickness? Well, we said the cause was that there was lower oxygen when you're higher up. So there's no oxygen for you to breathe, which means you have low oxygen in your blood, which means you don't get enough oxygen to your brain, which is why you feel like, icky. And so we can employ something called Shelias Principle. All right. Everybody pronounces this name differently. I'm never going to ask you to spell it. Don't worry about that. But it is an important concept. And basically what it says is if I have extra of something, then they're going to collide more often and form more of the opposite thing, right? And so basically when we disturb it, like if I add too much oxygen, the reaction has to shift to the right, just like adding too much B caused it to shift to the right. Okay, so here we have the reverse problem. So O2 goes down, so we're losing a reactant. That's kind of like this simulation, right? We lost a reactant here, and we see that it went from orange to yellow, so it went towards the left. When we lose a reactant, it shifts left, which means I've got more oxygen in my lungs that's not bonding to hemoglobin, which means it never gets to my muscles, which means I don't feel very good. Or my brain. That's really the problem, is your brain. And so you can feel really sick in those conditions. Okay, so we gotta, to fix it, I don't like complete sentences today, so. So what 2 things can be done? Okay, so number 1, we could add oxygen, right? Some way, either make it with a chemical reaction or bring a tank up with us or whatever. That's what a lot of mountain climbers do. They bring a tank with them. Astronauts bring supplies to make oxygen, kind of, similar to that KClO3 reaction we did in 111. So that's a handy one to have if you're stuck in space without oxygen. But anyway, also KClO3 makes a nice rocket fuel. We could add some oxygen. That's one thing we could do. Most people figure that one out pretty quick. You just, you don't have enough oxygen, so get more oxygen. And that's true, that'll fix it. The other thing we can do is a little bit weirder, a lot weirder. You can add more hemoglobin. So it doesn't matter which reactant you change. You could change oxygen or you can change hemoglobin. Either one is good. By the way, they do this by like drawing their own blood for weeks before a race and then injecting themselves with it. That's how you can make more hemoglobin. Or other more ethical athletes, that's called blood doping, by the way, if you're curious. It used to be a big deal. It's now illegal in most sports, but it's hard to trace because it's your own blood, so how do you know if they do it? But anyways, so you increase your own hemoglobin. Another way to do that is naturally by going to train somewhere high up. So a lot of the time football teams will go train in like Colorado because the mountains are really high. And after a while, your body starts to produce more hemoglobin on its own because it's like, this is out of whack. I don't feel so good. And that's why my student from the Peru mission suddenly felt better one day. Her body was just like, hey, we finally have enough iron to make more hemoglobin, so you feel good now, right? So the pro tip, if you're going to be traveling somewhere that's really high up, bring an iron supplement. Okay, you're going to need a lot extra to make more hemoglobin. Anyway, so the explanation here is if we add more oxygen or hemoglobin, we are increasing a reactant. Okay, which means we got to use up some of it. So it's going to, I left out a word, it's going to shift to make more of the hemoglobin where the oxygen is bound, right? And that's the one we need in our muscles. That's a B. I don't know what's going on over here. Okay, so by increasing a reactant, we're going to shift it to make more products, which is what we need to not feel sick. Okay, so this is a really, really important reaction. This is called the Haber-Bosch process. It is responsible for something like 1% of the world's total energy usage. So as of like 2012, it's probably higher now. So if you ever want to get rich, fix this. It's expensive, and here's why. It requires a lot of energy, okay, and a lot of pressure. And so we need this reaction. We can't exist as humans on Earth without it to produce ammonia, which is fertilizer, right? And so it used to be that the only way to do this was the old-fashioned way. You'd have to collect all the waste from your cows and your chickens and all of that and try to use that to fertilize your crops with. We don't have enough of that on the planet to feed the entire planet, all the fruits and veggies and stuff like that that we need. The grain especially is really has a high requirement for fertilizer. And even if you don't eat a lot of grain, by the way, the meat that you eat does. So it's all related. Everything comes down to needing ammonia in order to survive. And so the question is this exothermic or endothermic in this particular case? Go ahead and answer that one, right? Based on what we have written here. And how do you know? All right, so the question is, if we increase the heat, so we increase the heat, it's written here as a product, so we're increasing a product. Now I have too much products, so what happens? Well, if I have too much products, then I have to make reactants. According to the Shelias Principle, that would mean shift to the left. Okay, so in the reaction where heat is a product, we shift left in order to well, whenever we increase the heat. So in other words, if I wanted to make ammonia, increasing the temperature in the way that this reaction is written right here would only make it not produce ammonia. You'd get less ammonia that way, so maybe that's not the best option. Okay. In this reaction as written down here, this one, exothermic or endothermic? Take a look at that. Okay. And again, how do you know? Right? But if we increase the heat of this reaction, right, we're increasing heat, it has too much reactant now, so it's going to have to shift to make product. Now this is just for temporary until it's back to equilibrium, and then, you know, you go about your business. But in the end, we're going to end up with more product. And in order to make, you know, so like this increases, we increase the amount of NO2. In order to do that, we have to use this up. So it goes down. And that all happened because we just changed the temperature. So temperature can have a really profound effect on a reaction. One example of this is familiar to us because we live in upstate New York, and if you've ever gone trick-or-treating with glow sticks, you have seen this phenomenon. Also, it's a handy trick. It's like a life hack you'll see on the internet and everything. So like here's the reaction. Here's this big old carbon. Each one of these little hexagons is a carbon thingy. We get to learn about that in lab very, very soon. So, you know, just be excited for that. But each line where they meet is a carbon. So we have like 6 carbons right here. And the same thing on the opposite side and another carbon here. So lots of carbon around. This is an organic molecule. And it's a really reactive one. Symmetric also, which is beautiful. So when you break your glow stick, what you're really breaking is a little vial of glass inside of there that has hydrogen peroxide in it. And this begins our reaction. It breaks this in half. Bloop. I don't want you to be that way anymore. And, well, not exactly. That's actually a lie. Hang on. It breaks it in a different space. Let me just show you. Right. So we're going to make this ring thing with an OH on it. So what's really breaking is like basically these pieces. And what we're going to do is like connect these 2 oxygens. Okay. So we get 2 products. We get a ring with one of the oxygens and a new hydrogen that came from the hydrogen peroxide. And then, so we get 2 pieces of that because it's symmetric. You get one here and one here. And then the middle bit makes this nice little square shape. Now, square shapes have a 90-degree angle right there, which is really unstable. Those electrons do not want to be that close together, especially not in the oxygen. They're like way too crowded. It's very uncomfortable. So this thing is really reactive as soon as you form it. Any amount of heat in the air around it gets absorbed, and it causes this to break apart. And when it does, if you just, you know, break it up like that, you get CO2 and CO2, which is quite stable. So that's a good reaction. Okay. And when this breaks up, the energy goes into a dye, a big organic dye, even bigger than this one. And once it absorbs that little bit of energy from breaking up into CO2, it glows. Okay, so I want to ask you a hypothetical. If I increase the heat here, say I put it into like boiling water, for example, what's going to happen? Or what if I freeze it? What if I put it into some ice water? What's going to happen? You ever do that? You ever take your glow stick and put it in the freezer? What does it do? Okay, I'm going to leave you to ponder that. We'll discuss it briefly in class. In the form of a demo. I'm going to show you. I'm going to show you what this does. Okay, so to summarize Le Chatelier's principle, which is the idea that when something is at equilibrium, if I mess it up by changing concentration or temperature or pressure, which we haven't quite got to yet, but if I change anything about it, it is going to compensate for that. All right, so if we add more B, increasing a reactant is going to mean we have to use up reactants. So it has to shift to the right to do that. Okay, that means if I use up the reactants, that has to go down. So this is what I did to it. Okay, so this is me. I messed up B. In order to shift forward, we have to use up some A. That's going to decrease, and so this one is going to get bigger. We're going to get more product out of that. Okay, our ratios still become equal, because we have a lot more B hanging out there. But I'll have less A because it has to react to get to product in order to balance the scales. Similarly, if I added a bunch of A, boop, that's still adding a reactant. So the same thing happens, right? If we increase this one, and I got too much of it, I'm going to react it with the B and produce some AB. So it still shifts right. Okay. All right, so what about if I take away, so I'm going to decrease the amount of AB, right? So that's the change I'm doing to it. I'm taking away some, decreasing it. Now I don't have enough product, so the reaction has to go this way. We have to make more product. So A and B are going to react, and I'm going to get some AB, so it's going to shift right again. If you don't like lefts and right, if that's hard, just say forward. Right? The reaction is going to go forward. Or if it shifts this way, that would be left. We could say it's going to go backward. Whichever one you're comfortable with is just fine. Or I guess even if arrows feel comfortable for you, that's fine with me too. Okay? So if I add a reactant or I take away a product, I'm going to shift right. So then of course the question is, what do I have to do to make it go to the left? Maybe I want the reactants to be separate. Well, there's a couple things. You could increase the product, or you could decrease any one of the reactants. Both of those are going to cause it to shift back towards A plus B. Okay, I want you to fill out this summary sheet here, and hopefully it makes sense to you at this point. Okay, so if I add more reactants, what does the reaction do? Again, arrows or words, whatever works for you is fine. Okay, and then down here, an exothermic reaction has a temperature where heat is a product. It's a product. Exo means out. The heat is going out of the reaction, so it's product. So if we increase the heat on a product, it's going to shift the reaction to the left, back to the reactants, because it's a product. When we increase it, it's got to go backwards. An endothermic reaction is going to be the opposite. So it's got heat as a reactant. We have to put it in to make it go. And if I increase the heat, it's going to shift it to the right. Okay, so hopefully you follow that logic. Now the last little bit that we have to learn about Le Chatelier's principle is the idea of volume changes. Okay, so first off, what is pressure? This comes from the gas laws chapters. We had 2 of them back in the beginning of this semester. But basically, this is how I think of it. You might have a different definition. That's cool, right? Whatever you want. Right? But basically it's the force exerted on a pressure on a container by a gas. Well, so that is usually measured in atmospheres or torr, or which is the same thing as millimeters mercury, psi. Like there's a whole bunch of units. Okay, these are the most common. Also bar and Pascal. All right, so let's think about this. If I increase the volume of a reaction when we've got a gas, what does that do to the concentration? Okay, so let's just draw a little sketch, right? So let's say we start off with this much space in our container, and we just have like, you know, a few particles, whatever. They're gases, they're hanging out, they're all spread out, like that. So the question is, if I move this up, if I make it a bigger volume, so something more like, you know, like a bigger container, what happens? Well, we got 6 particles there, right? Do they look more concentrated or less? They look less concentrated. They got more room to spread out, right? It's like if anybody has a sibling, this is like sharing a bedroom over here, and then suddenly we move to a bigger house and everybody's got space. That's nice, right? So we have increasing the volume decreases concentration, and it also decreases the pressure because now there's much more space. You're not under so much stress when you get a bigger house, and you don't have to share your room with your sister. I mean, sibling. True story. Okay. So changing the volume, it does the same thing as changing the it changes the concentration, right? Increasing the volume decreases our concentration. And so also the opposite would be true. If I increase the volume, or sorry, if I decrease the volume, I'm increasing the concentration. And also pressure. So that's a relationship that we should keep in mind. All right, and so this is a complicated question. It affects equilibrium in different ways. It's not, we can't say shifts left and shifts right because that doesn't work. It's specific to a given reaction. So for example, let's see if we can figure out how this works. Initially, I take 2 nitrogens and 6 hydrogen molecules and I put them in a container. Hang on. Okay, there, I fixed my labels. So here's our initial conditions. At equilibrium, we have 1 product and, you know, a whole bunch of... Okay, so now we still have 1 of our nitrogens hanging out here and 3 of our hydrogens, but we have 1 product that has formed as well. That's our equilibrium position. It's a mixture of products and reactants together. In a perfect world, we would get all ammonia from this because, again, that's the thing we're trying to make. That's the thing that dictates whether people eat or not. So we would like to have just like all ammonia. It's impossible. But there are things we can do to make it better. Okay, so when we look at how many molecules there are on each side, we're going to look at the balanced reaction here. You could count them from here. It's doubled from the balanced reaction, but it's easier to not have to draw a picture every time I need to picture what's going on, even though that's the mental picture I've got in my brain, right? But on this side, we have a total of 4 particles. If we were in the initial condition, we would have 4 particles total. On this side, the final would have 2, if we could get it all the way over there, right? So we're comparing 4 particles on the left and 2 on the right. Okay, and that's a comparison. Now, if I squish it, does it look more comfortable to be in the initial position or in the final position? Well, if this was my siblings and we moved into a smaller house, I kind of feel like that's pretty uncomfortable. Everybody's like, you know, all in everyone's space. It's pretty uncomfortable. Over here, this situation's a little bit better. This is like when I moved out and I was finally able to have just like 1 roommate with her boyfriend, which is a great way to save money, right? Because I get more rent from 2 people than 1. But we didn't, you know, they shared a room, so it was more comfortable for me. I got my own room, which is great. Everybody should have their own room. So this situation is better for when you have a smaller volume, right? So we decrease the volume. This one looks better. There's more room. When a molecule forms, it occupies less space than its individual elements do. Right? So this is very, very crowded. This looks a little bit less crowded. That's better. So when we decrease the volume, it's going to shift the reaction to the less crowded side, or you can even say the fewer particles. That's probably better grammar. Sorry, English teachers. It's not you. It's my fault. Okay, so we're looking for where there's less crowding. That's more comfortable. So in this particular reaction, we have 4 reactants and 2 products. The way that this is written, and so we could say it's going to shift when we squish it. We decrease the volume. It's going to shift to the right because there are fewer particles on the right, and that's more comfortable. Okay. Now, the thing about equilibriums is because they happen in both sort of forward and backward at the same time, it is equally valid to write this reaction. They both are the same thing, okay? So I can't say that in every situation, if I decrease the volume, it's going to shift right. We can't say that because I can write the reaction the other way, and now suddenly 2 reactants and 5 products, 4 products. So in this version, it's going to shift to the left, okay? So we can't make sweeping directional statements here. All we can say is that if we decrease the volume, it's going to want to be less crowded, and so it's going to go toward fewer particles. So we just look at the balanced reaction to figure out which one is fewer. And so it depends on the reaction. A couple of quick notes. Changing the volume or the pressure, either one, or the pressure, right? So pressure and volume are opposite, so if I like decrease the volume, it means that I have increased the pressure. Okay. it's only going to affect things with gases in them, because liquids and solids are not compressible. So changing the volume of them does not matter. Okay. When you decrease the volume, you're basically increasing concentration of gas molecules, and that means it's going to shift to fewer particles. Again, you'll note I'm not saying left or right, because we can't. The reaction can be written either way. And depending on what I'm trying to illustrate, I write it either way, okay? If I increase the volume, that's like decreasing the concentration of all the gases. So in other words, we're giving them more room, which means the reaction is going to shift toward the greater number of particles, whichever way that is. Again, not saying left or right, because it just depends. If we happen to have a reaction where all the gas particles are the same, nothing happens. All right. So we briefly talked about catalyst in the beginning when we were looking at like the height of this ruler, and I told you that you know, we got a forward reaction here with a big hill, but then once you get up here, it falls down even bigger. So this is an endothermic reaction because our energy at the end. Ooh, that was wrong. Sorry, that's confusing. This is an exothermic reaction because the energy at the end is higher than where we started. So this goes down. So you can just kind of think of it as energy is negative here. We're producing it, giving it away. So that's exothermic. Now if I put a catalyst in, it means it's easier to go forward, right? Not as big of a hill, right? If you think about it as a bicycle or pushing a ball up a hill. Not too difficult now because a catalyst lowers the activation energy, and it does this by positioning things precisely right to make them react, to make them collide properly. Okay, so we decrease the hill. But the thing is, if you decrease the hill in the frontward direction, you also decrease the hill in the reverse direction by the same amount. So you're not going to make more products or more reactants by adding a catalyst. All you're going to do is speed it up. Okay, so in other words, it comes to equilibrium faster this way. We've seen some catalysts before. We've used, we actually used MnO2 in Ch112. It's the big green troughs you guys use to make oxygen. And it's the same reaction here. You take hydrogen peroxide, it produces water and oxygen. And this happens all the time anyway. A catalyst just speeds it up. And that, by the way, is the reason hydrogen peroxide has an expiration date. For real, it does, because the oxygen's going to evaporate from your bottle and then you're just left with some like really clean water. Which is better than nothing, I suppose, but it isn't great for cleaning wounds. It's not going to kill any bacteria. So anyhow, hydrogen peroxide decomposes to form water and oxygen. And you can make this go fast in a variety of ways. You can use a catalyst MnO2 like we did, it's that black powder. Or you can use another catalyst called potassium iodide. And this one works just as well, maybe a bit faster. It works because the I- reacts with the H2O2 to make water. That's our first one of our products. And this stuff, iodate ion. And then that's going to react with another piece of hydrogen peroxide to produce another water, and also two oxygens, one from here and one from over here. And we get our catalyst back. Right? So we started with I- and we get it back. So catalysts are not used up in the reaction. They're made again. Okay? That's an important catalyst fact. And it makes them handy because I can reuse catalysts, which is great. That's exactly what we do with that MnO2 black powder. We filter it out, we use it again. No reason to waste it. So now, the final part is about buffers. And this is one of the most, without a doubt, important parts of Ch112 because buffers run your body. Without buffers, we would all have been dead before we were even born. So it's pretty important to understand this. And my A&P students have come back to me, the ones who did well in A&P, you know, and they tell me that this is the most important topic. This and the shape thing, the hydrophilic thing. So if for no other reason, pay attention to this now, because when you see it in A&P, it's going to be easier. In order to make a buffer, what we need is two weak things, a weak base and a weak acid. Okay? So we want to have two weak things together. right? So you can make one with a weak acid and its conjugate, which isn't going to be a weak base. Or you could go weak base, weak acid together. It doesn't matter. The important thing is that you have an acid and a base present in pretty close to the same concentrations. And what it does is it resists changes to pH if I add a strong acid or a strong base. Because if I add a base, it's going to react with this acid instead of, making the pH go up immediately. And if I have an acid that I want to put in, it's going to react with the base rather than, making the pH go down. So it's perfect. That's what a buffer does. Doesn't matter whether you add a base or an acid, there's something there that will react it instead of making your pH change dramatically. Every time you eat, you're adding H+ into your body. That's what is produced during metabolism. It's unavoidable, it's normal. That's just a reaction, okay? Don't freak out. It's not going to matter because your body has a whole bunch of buffers in them. So for example, your blood has something that is also in the ocean. It's called the bicarbonate buffer system. This one is essential for maintaining the pH of human blood and the ocean, which actually have different pHs because they have different amounts of each part of the buffer. Also, when you take microbiology, there's buffer in the growth media, and if there's not, the organisms don't live because as soon as they start growing, they produce H+. Everything growing produces acid, okay? Not like LSD acid, I just mean like H+, okay? Just to clarify. You're not producing LSD. That would be weird. Anyway, bugs growing on an agar plate produce acid, and if there weren't a buffer in your plate, if there weren't something in there to keep the pH from changing, it would get too low and whatever was on there would die. Most of your beverages are contain buffers. For example, I just happen to have a Diet Pepsi my husband left on the table here. It has water and caramel color, aspartame, so that's the sweetener. It has phosphoric acid and potassium benzoate and citric acid and something else. I don't know what that is. Oh, that's part of the buffer too. Acyl sulfame potassium. Okay, so what we've got is benzoate and citric acid. One of those is a base, the benzoate, and the citric acid is an acid. If you go look in like juices, it'll say stuff like citric acid, which is delicious, by the way. We love it. Comes from oranges and lemons and stuff. And the other half of that would be something like sodium citrate or calcium citrate or whatever. It doesn't matter what this is. This is a buffer that maintains the pH of many, many juices, like orange juice, apple juice, all that stuff. They put it in there so the pH stays pretty low because if it gets too close to neutral, you'll have mold in your beverage, which is gross. So buffers are useful. Okay, and when we talk about buffers, there's this idea called the common ion effect. And basically, if I put in some sodium acetate, it's going to make acetate, right? That's the important part of that. The sodium does nothing. It's a spectator. But if I take my sodium acetate and I put it in, it's going to make acetate in there. And I put also acetic acid. This is the conjugate, so this is acetic acid right here. Right? That's the name of that stuff. If I put acetic acid and sodium acetate together in water, that's a buffer because I have acetic acid and I have its conjugate. Now, if base is added to this, so if I add OH minus, that is going to react with the acid. Now, sometimes people are tempted to see the OH plus on the other side over here and think that it might react there. But the thing is, there's like a lot of acetic acid and only a little bit of H plus. So it's going to react with the thing that's more concentrated. And so when it does, in this reaction, it's going to produce water. The base pulls off this hydrogen, and it's going to produce acetate. Okay? So bases always look for the most concentrated acid, and that's acetic acid in this sample. And it's going to produce the conjugate. So we're increasing the amount of this stuff, so we're going to shift back this way. So basically, by reacting acetic acid, we've made acetate, and now it's going to shift back and make a little bit more acetic acid. So overall, we have a very small pH change because all of the H plus we put in has reacted. It didn't increase the pH that much. A little, because we did make a little bit of acetate, and by shifting to the left we are going to decrease H plus. So the pH will go up a little bit, but not a lot. If we add acid, the acid is going to want to react with the base, and there's only one of those here. That's the acetate. And when that happens, it's going to produce acetic acid, right? Okay. Well, so if we produce acetic acid, let me just get this out of the way. Okay, so we're producing acetic acid. That means I am increasing a reactant. So the reaction shifts to the right. And so the pH is going to go down a little bit, right? Remember, we're going to, well, so let me just clarify. H plus goes up, which means the pH goes down. The more H plus we have, the lower the pH is. So we increase the amount of H plus by a little bit, but not as much as what we put in. By a little bit, because the initial amount reacted, and it's only going to form a teeny amount of acetate. It doesn't form all, because this is weak. Okay, so in either case, whether I'm reacting with an acid or base, there's not a dramatic change in pH. So what we have here is that bicarbonate buffer system I was talking about. This is the one responsible for keeping the pH of the ocean consistent, or at least mostly consistent. It's responsible for your blood pH, which is pretty consistent. Okay. By the way, it doesn't matter what kind of freaking water you drink, just putting that out there. There's a lot of rumors all over the internet about drinking alkaline water. It doesn't do anything to your blood pH because you have buffers. Okay, good. Glad we got that out of the way. Just so you know. Okay, anyhow. So this is the bicarbonate buffer system. And so the way it works is CO2 dissolves in water to produce carbon dioxide that's dissolved. That reacts pretty quickly with water to form something that's called carbonic acid. This is what Sunset Carbonic sells down on the road. They sell it to like restaurants that have, you know, so it forms carbonic acid. They sell that to restaurants that have, you know, carbonated beverages, because that will also, this is actually an equilibrium, right? So if you form carbonic acid, it's going to make CO2, which is bubbly and delicious. Okay, so anyways, in the ocean, the carbonic acid pretty quickly breaks down to form a hydrogen ion and something called bicarbonate. Bicarbonate is basically baking soda, right? Baking soda is sodium bicarbonate, but, you know, same kind of idea here. So you can make a buffer right in your kitchen if you've got some carbonated beverage and some baking soda. That's all you need. But anyhow, so this is bicarbonate, and so this is called the bicarbonate buffer system because it's kind of the central piece. It's the one in the middle. Now, if we keep adding more and more CO2, more and more CO2 dissolves, and so we're shifting, you know, we're shifting this first reaction to the right, which means I'm increasing carbonic acid, so it's going to shift right again and make more bicarbonate. And so as we make more bicarbonate, you'd think we could shift more and more to the right again and make some carbonate here. This is carbonate ion. The problem is that the ocean already has as much carbonate ion as it can fit. So this one can't go any farther. We can shift this one to the right, we can shift this one to the right, and that's where it ends. We can actually continuously keep dissolving more bicarbonate in the water, and it's going to continuously increase H3O plus, which is acid. So this is called ocean acidification. And so as CO2 levels rise from producing, you know, manufacturing things in on our planet, as CO2 levels rise, we see more and more CO2 dissolve, and more bicarbonate forms, which also produces hydrogen ion. And this is a problem because all these little creatures, so this picture shows snails, you know, all these little creatures depend on having the right pH to live. Fish and coral and all kinds of stuff. If it's too acidic, they die. If it's too basic, they die. And it's no good. Sometimes students will suggest to me, well, why don't we just take out some of the carbonate so it's not saturated anymore? So we can't take out the carbonate ion because actually these shells start to fall apart too, because they're made out of calcium carbonate. which is what's in the ocean and the sand and everywhere. And so if we took it out to allow this to continue shifting, it would just build up more and more hydrogen ion, because that also produces hydrogen ion here. But also the shells would start to become deformed and broken because they need to be saturated in carbonate. So anyway, we just keep building up more and more acid, and this kills reefs and fishes, and it's terrible and awful. But good news, a couple of years ago, we finally stopped producing more and more CO2. I can't remember what year it was. I think maybe like 2015-ish. For the first time ever, our global CO2 levels did not increase for 1 year, 2 years actually. This past year, the climate report is not good. It increased again. Okay, so some of the measures we were using were working, and then governments backed off of that, and now they're not working, and it's really a bad thing. So anyways, go vote. Be educated. Stop people from destroying our world. By the way, why do we care about the pH of the ocean? Oh good, I'm glad you asked that. The reason is because in the ocean are a whole bunch of algae. They're microscopic little plants that float around. And it turns out most of our oxygen in the world comes from algae. Okay? And they're very pH sensitive. So if the pH continues to be acidic, all the algae continue to die, and they don't produce oxygen as much as we need, and we will die too. That's the short, quick and dirty climate science version. Okay, so when I was in graduate school, my advisor said that I needed a hobby. She felt like I was working too much. So I got a hobby. I started keeping artificial saltwater tanks. So this is really a picture of one of my tanks. Taken around 2010, I think. There's some corals over here. These little guys here are called mushroom corals. They're pretty cool. These are called zoanthids. There's a little shrimp hiding out down here in his little cave. They're ambush predators, so they like to hide out. There's a couple fish. So lots of life in here. There's also some algae. You can see there's some green streak right here. That's algae that's growing on the tank, and that, you know, adds a little oxygen to my house, which is great. Now, if you put straight up pure water into a fish tank, it will have a pH of 7. What do you think will happen if we add some, I don't know, HCl into this? Does the pH go up? Does it go down? Does it stay the same? What do you think? On the other hand, if I buy the expensive manufactured buffer for saltwater tanks, they have a pH, you can adjust this, but basically it's about 8.4, so it's a little bit basic. It's buffered though, so what's going to happen in the pH if we add acid? Same amount as in the first part of the question. Okay, so pause the video and give those a quick answer. Well, here's the answer. A guy named Randy Holmes Farley has made an entire career out of studying how saltwater aquariums work. And so here's some information. If we have pure water, that first drop of acid changes the pH from 7 to 4. And it only goes down from there. Even if your pH changed from 7 to 4 on your skin, that would hurt, okay? Fish can't survive pH changes that big. They all would die. The whole tank would be dead if that happened. One little drop of acid is enough to do that. If you use a buffer though, it goes from about 8.4 to like maybe 8.3, and then another drop is like 8.2. And we get some more dramatic changes in here, but you get a little bit of a buffer. You get a zone where the pH doesn't change very much. That's what a buffer does. It prevents pH from shifting a whole bunch when you add a base or an acid to it. Okay, so that's important, because if the pH changes dramatically every time a fish poops, which is a base, right? Adding a base to it would increase the pH. It would kill your tank. You'd never be able to raise a fish, right? And so that would be terribly sad. All right. So to summarize, when you have a buffer, by the way, a buffer is when you have a weak acid and its conjugate base, or a weak base and its conjugate acid. If we add a strong acid to to one of our buffers, so like let's just take an acidic buffer. So here's HA is the acid and this is the conjugate. That's one way we can show it. So it'd be like something like let me think. I don't know, HF and this stuff. So if that was our buffer, okay, I put in some fluoride ion, I put in some hydrofluoric acid, that's our buffer. Okay, if I add an acid to this, it's going to react here. All right, so instead of just pouring H+ into the water and making the pH go down, what it's going to do is it's going to react with the base here, which is going to form some HA. We're just going to shift back a little bit. So overall, we're going to get a slight change in pH. It's going to go up a little teeny bit, as opposed to, it's a teeny arrow, really teeny. Can't get it to work. As opposed to just dumping a whole bunch of H+ in and the pH goes like, you know, crazy. Same buffer system. If I add a base to it, it's going to react with the H+, right? So just to clarify, in this one, this is basically the reverse reaction, right? We're increasing our leftward reaction. And this one, if we put in a hydroxide, it's going to react with the acid, which is HA, and we're going to form some conjugate. And neither one of these two have a really big dramatic effect on pH, so we're good. The pH changes a little bit, but not a lot. And then in our base buffer system, if I add acid, it's going to react with the base to make the conjugate. And if I reacted the hydroxide, so if I add a base to it, it's going to react with the conjugate and form more of the original base, right? So, you know, really the reaction that would be happening would be the reverse one, like this. And so since our products are water and our original B, that doesn't change the pH at all. So, I mean, you know, not very much. It'll shift back a bit, but basically adding a base doesn't dramatically change the pH if you have a buffer there. It would if you don't, because then you're just dumping in a whole bunch of hydroxide. Okay, so that's it for equilibrium. When you have questions, feel free to reach out to me and I'll help you work through them.